it. Okay, we're recording now. So again, the ball, when you kick it, you apply a force in this direction, which gives an initial velocity, okay? And when kicked at an angle, the ball will actually travel in a curve, not in a straight line. That's because of G, gravity. The gravity is going to continuously pull on the ball downward at any time or any point of the flight until it will reach the ground, okay? And if you go to a higher position, let's say at the top of a building, when you kick a ball at the angle, same thing. It will travel in a curve and reach the ground, okay? Even if this angle is 0, if you kick a ball horizontally, okay, what's gonna happen? It will still curve downwards like this. That's because gravity is constantly applied on the ball, okay? The path of the motion is called trajectory, and the object that moves in this type of motion is called a projectile. And this is what we are going to study, okay? Now, how are we going to do it? Well, first, these are the rules. Now, let me show you in the simulator what are the forces that are being applied on our projectile. So let me open my simulation from here. Okay. Instead of lab, I will go to vectors. Okay. If we look at the forces that's being applied on our projectile, let's have a cannon here with an angle of 50 degrees. That's the initial speed. Okay. And let's remove the air resistance or the friction with the air. When you fire the projectile, as I said, okay, as you can see, it is actually moving in a curve. Let's remove that one, reduce the initial speed by, let's say, 15. I want to show the curve on the screen. Okay, so if you look at it, what are the forces that are applied on the ball? Okay, it's not very clear. But if we put the components, okay, instead of the total forces, oh wait, let's put the velocity. There you go. You can see that there are two vectors, okay, which is being applied. One horizontal and the other one is vertical. Okay, let's fire a second ball. Let me fire 3. 1, 2, 3, and pause it. There you go. As you can see, depending on the position of the ball at the curve, at the trajectory, one of the forces or one of the vectors is always in the same direction. That's the horizontal component of the velocity, okay? What about the other one? At first, it's pointed up. It will reach a certain point where it will be almost or 0, equal to 0, and then straight down, okay? That's the y component of the velocity. So as you can see, there are two components of the velocity in the projectile motion. Okay, the x component and the y component. And these two do not affect each other. How do we know that? If we increase the initial speed, okay, increase the initial speed, woof, you can see that the value of the x component here, the horizontal line, is not changing. It's constant. Okay, and the value of the y component is changing, but depends on the position of the ball in the trajectory. Why is that? Imagine if you throw an object straight up. Okay, let's change the angle of our cannon. Let's make it 90 degrees. Let's go back to 15 meters per second initial velocity. Whoop, too close. There, and let's fire. What happens to the x and y component of the vector? Because we are firing straight up, there is no x component. Okay, let's increase. Let's make it 20 again. And you can see that at the top of the flight of the ball, what happens to the velocity at the top? It will go to 0, and then the ball will fall down. And if you change the angle, you will actually see that you will actually see the motion, the velocity on the y-axis is actually the same, going up and then going down. Okay, you can see that it's actually the same, the velocity going up and then going down. It shows us that the x and the y component of the velocity of the vector is actually independent. They don't affect each other. Okay, they do not affect each other. However, if we look at the equations, how are we going to use it in our experiment today? Let's go back to the data sheet. Because the x and the y component of the vector do not affect each other, we can take advantage of this to calculate our objectives. What are our objectives? Number one, or well, not really number one. Number three, horizontal range of the ball. When we say horizontal range of the ball, how far the ball will travel? That's x. Okay. And what's the other one we will calculate? The maximum vertical height of the ball. That's on the y-axis. Therefore, we can use the equation for the horizontal component and vertical component of your vectors to find the maximum height and the range of our projectile. And these are the equations. It's the same as the analytical method to find the x and y component of your vectors. Okay, if you remember the objects in equilibrium experiment. Anyhow, using the horizontal component of velocity of the projectile, we can simplify how to get the range by using this equation, equation number one, where x is equal to, wait, my pen is not working properly, x is equal to VO cosine theta, theta being the launching angle, and t is the time of flight, the time it takes for the projectile to move across the air. Okay? What about the maximum height? Is there a way to find the maximum height? Yes. But first, to find the maximum height, we must find what we call the velocity of the projectile in the vertical direction, Vy, okay? And we use the acceleration experiment. If you remember the acceleration experiment, this is the one which you use in horizontal. I don't know if you take this in theory already. The original equation here is Vf squared is equal to Vo squared plus 2ab. But we make it in the y-axis. Yes, you had the quiz on this? Okay, good. So if you make it in the y-axis, this becomes Vy, this becomes Vy, and A becomes G, gravity instead of acceleration. Okay? It's the same rule, Shawab. It's the same. You don't have to memorize any rules here. Okay? Now, because from this equation, we can actually take the maximum height, which is y. Okay? What's the equation we are going to use for the maximum height? This one. This is the simplified equation for the maximum height. Again, no need to memorize it. You can simply go back to the main equations for your velocity and accelerations. Okay? Now, how are we going to do the experiment? Let me show you. Before we can simulate it, I want to show you, oops, let's clear everything from here. I want to show you the actual experiment video, okay? This is the video which I sent you in YouTube. I don't know if you watched it, but if you didn't, well, here it is right now. So this is the projectile launcher, okay? In front of the projectile launcher, there are two photo gates, here and here. These two photo gates will detect the movement of the projectile. This is the projectile we are using. It's hadid, a steel ball, okay? When we set the angle using this degree scale with the string right here, okay? When we fire the projectile will pass through the 2 photo gates, and the time it takes to travel between 2 photo gates will be measured by the computer, okay? And the distance between the 2 photo gates is actually 10 centimeters. What I'm giving you now is the information for you to make table number 1, okay? Let's go to your table number 1 from your data sheet. In table number 1 from your data sheet, you will set the angles, okay? Any angles will do, but we have chosen several angles to make it more simple. The distance between the photo gates is 10 centimeters. Can anyone tell me how much is this in meters? Yalla. Anyone? Can anyone tell me how much is this in meters?
0.1.
0.1.
0.1. How did you get that? So that the others will understand. You divide by?
Divided by 1.
100. Okay. Said is correct. Divided by 100. So it's actually 0.10 meters. The time between the 2 photo gates will be given by the software, and the muzzle velocity, how fast the projectile will escape the gun or the launcher, will also be given by the software. You will calculate the same number using the equation VO, okay, equals D over T. Which D? D over T. So let me go and fast forward to the time where I'm measuring the speed of the projectile. You can see when the ball is passing through, this light will turn on, okay? Okay, launching the projectile. I want to show you with the data. So this is the data, okay? The time it takes to cross or to pass through the 2 photo gates and the measured velocity of the projectile. Okay, that's
In the first table, we are not going to use the time manual
fast forward. Okay.
to record.
See how fast
Launch
it
the
will travel.
projectile by pulling the trigger and taking a reading from your computer. Make sure that you
Okay, Shabab, this is the reading that we will use, okay? 0.03 seconds. Let's go to our data sheet. Time between the 2 photo gates, 0.03 seconds. Is that correct? Yep. And then measured velocity, 3.31 meters per second. Okay? The next thing you will do is simply to calculate this. Is that clear, Shabab? Is it clear? Okay, I need to know that everybody will be able to do it. Okay? Yes, Said, what is your question? I cannot read Arabic, I'm sorry. Okay, good. Now, is that yes in Arabic? No, I can read no in Arabic. It's easy. Anyway, Shabab, let's continue. What happens when we change the angle of our launcher? Okay? I will ask you a simple question. If you have done hunting before, okay? You take a gun, for example, or a rifle, and you shoot at a lizard, straight. And you shoot at a bird which is flying in this, or maybe sitting on a tree. Will the speed or the velocity of the bullet change? Anyone? Are you sure, Fahad? When you change the angle, you have AK-47, for example. You shoot horizontal and you shoot vertical, you shoot at 45 degrees. The bullet of the AK will become slow or will become fast or will remain the same when it comes out of the gun. It remains the same. Again, Said is correct. Okay? How do you calculate error? I will show you later how to calculate error. But anyhow, the important part here, Shabab, is actually not to waste the time in table 1. Okay? So we will cancel all of this. It's not useful for us. Why? Because the muzzle velocity of our launcher will remain the same or almost the same, affected only by friction. Okay? It will remain the same. The results here will remain the same each time, even if you change the angle of your projectile. Clear? Even if we change the angle of the launcher, the velocity will remain the same. So table 1 is actually not very important. The more important part is table 2. Anyhow, how do you calculate the percentage error? Let's answer the questions. If you go down to the next page, here, that's how you calculate the percentage error. Calculated value minus measured value over calculated value. Multiply everything by 100%. Make sure you are using absolute values. So here, calculated value minus measured, divide by calculated, multiply 100%. Is that clear? So you will do only 15 degrees, and the data is already on the screen. Is that clear, Shabab, before we continue? I want to make sure everything is clear before we continue. What about the others?
Clear, Doctor.
Okay, maybe I should check the attendance now again. Yalla, come on, you have to participate, okay? Let's go to, what is +1, Waysam? Waysam, I mean, I agree with the others. Oh, okay, sorry, I didn't know that. +2, so we will get +3 up to +15. Okay, thank you. Let me just drink. Yalla, now it's time to do the simulation, okay? So you will use the simulation in table number 2. But we will change one angle here because this angle is not useful, okay? Instead, I will make challenge for you. This angle is a question mark, okay? Not 15 degrees. Why? If I go to my simulation right now, you will see that my cannon will not go below 25 degrees, okay? But it can go 90 degrees, so 30, 45, 60, and 75, I can find it easily, okay? But not 15 degrees. What are we going to do? We go to lab, okay? You can open the software now if you're on PC, if you want. You can open it now, okay? Make sure that our air resistance is not checked. This one is open, okay? Make sure gravity is 9.8, this number. That's the standard gravity for the Earth. And the only thing that you will change is the angle. And the initial velocity, we will use 20 meters per second. Okay, let's go to our table. In our table, muzzle velocity, 20 meters per second. 20, 20, 20. Okay? Mohammed Samir, we will check the attendance again later. So make sure you are present. Okay? So again, the muzzle velocity, 20 meters per second. What else? What about the launching height? Well, we can adjust the launching height of our simulator. So simply, you take this plus sign and you move it up. There. Is there an effect of the launching height of our projectile? Okay. Well, there is. If you fire the projectile, okay, and then change the height to, let's say, 2 meters without changing anything else, obviously, your projectile will reach farther. As you increase the height, your projectile will have a higher range. Okay, that's the idea about the height. So for us, we will simply keep it 0. Why? Let's go back to our data sheet. To get the maximum vertical height, you have to add the original height. If the original launching height is 0, then you can cancel this from the equation. So we can keep it 0. Okay, 0, 0, 0, 0, 0. The only thing left is to measure the time of flight, calculate velocity, vertical height, calculate horizontal range. What about this one? You have to measure the horizontal range as well. Okay, and then make percentage error for the horizontal range. So how do we do it? Let's start from 75 degrees going down. Okay, go with the simulator. Where's my simulator? There. And then make 75 degrees. Okay, and then this is 20 meters per second. And fire the projectile. Boom. Woof. It's so high. There you go. You can always zoom in and zoom out. Okay, it's just like playing actually. Now, what are the things that we can measure from here? we actually have a measure for time. Okay, how do we measure for time? We use this tool. This is the smart tool for the simulator. It can measure time, range, and even height. Okay, but we need only the time for now, at least. You take this crosshair, just like our smart tool, and place it where the projectile will land, and it gives you the time, 3.94 seconds. Go to your data. What's the time of flight? 3.94 seconds. What's the next thing that you have to measure? Horizontal range. Okay, go back to your simulator. What's the horizontal range? 20.39. Let's go back. Horizontal range measured 20.39. Everything else you have to calculate. Is that clear, Shabab? Is that clear? I need to know if you see how I can use the simulator. It's just like playing a game. You can have fun with it. Okay? Okay, Shabab? What to do next? Go back to the table, calculate this, and percentage error. Remember the percentage error, calculated value minus measured, divide by calculated value, absolute, multiply 100%. Okay, so that's the idea for the percentage error. So this three with the tick, you have to calculate them. Once you finish one line, go and do 60. Okay, let me show you 60 without changing the velocity, without putting anything else here. Just change the angle to 60, and there you go. Oop. Fire away. Okay, if it's too big to see the range, you can always zoom out and measure the time and the range. Once you finish 60, go 45. Fire. I will remove this one now. Okay. Go to 30. Fire. It actually looks nice. Okay. And then the last angle, this is your challenge. What's the last angle here? Not 15. Okay. Is it possible to find an angle that will match 75? Let's see. If you will notice, the angle of, let's make a screenshot of this. 1 second. Let me open my snipping tool. Where's my snipping tool? There it is. You don't have to measure it now, Wesam. You will do it by yourself, one by one. Okay. I want to show you something here. Look at this angle. This is 75. Okay. This is 60. This is 45. And this is 30. If you look at 60 and 30, they will land almost in the same place. Can we have an angle where we will land at 75 degrees? Let's see. Okay. Let's try the smallest angle, 25. If we fire, nope, this is far away. But actually, if you have an angle lower than 25, we can make it land here at 75. Okay, Kalas, because we cannot find it, let's just use 25 degrees. Okay, in the first table, let's just use, well, I was hoping that it's possible, but no. Let's just use 25 degrees here. So measure all the time, calculate the maximum height, calculate the horizontal range, measure the range, and then find all the percentage error. All by using the simulator. Any questions? Do you want me to send the link again?
No,
Yes, go ahead.
I open it in another window.
Okay,
you
good.
can lift it up the cannon like 1 meter or 2 meter, and you can go even minus an angle.
Yes.
So
you can lift it up like this. Ah, you mean this angle here?
Yeah.
Yes, that's correct. But we have to launch from 0.
Okay.
Okay. You can. I know you can. Okay. You can lift it as high as you want or below. Okay. But the thing is, why we want to, let's reset everything. Why we want to launch at 0 is because of this equation here. Y initial is the height of the cannon, okay? But in order to simplify this rule, we can remove Y initial by making this 0, okay? That's the only reason. Okay, Shabab, any questions? What to do next? What to do? That's it. This is the experiment. You've finished the table. You're almost, let's say, 90% of the report. But what's next? Okay, let me explain to you what's next. First, when you go to this page, okay, this page, you have nothing to do here. Mafi, there's nothing to calculate here. Clear? What is the use of this page? This is only for notes. This is only for rules. This page is only to get the rules. What rules? Rules for the error. Rules for the maximum height. Rules for the horizontal range. And again, for the error. Okay? There is nothing to calculate here. Is that clear? Shabab? Is that clear? Okay. All the calculations, you will simply put the final answer here. No need to show the steps. Okay? Once you finish the table, what's the next thing that you have to do? Well, first, you have to make a graph. So on a graph paper, you have to draw 3 trajectories. When we say draw, that means you have to use your hands. You have to use pencil, okay? Which angles are you going to draw? 30, 45, and 60, okay? How are you going to draw it? Because we have no Y initial, you will simply draw on a horizontal your 30, your 60, and your 45. It will look like this, okay? But you have to be accurate with the angle. You have to be accurate with the horizontal range. Now, teacher, how can we draw this one? Look at the simulation. What's the horizontal range? It's in meters, okay? If we fire, you will see that the horizontal range is in meters, right over there. What's the range? 30 meters. Is there a way to draw 30 meters? Sure there is. Here's what you will do, okay? I will go and open this empty page. You will make what we call a scale. What scale are we going to use? For every 10 meters, for example, you can use 1 centimeter. And because of that, if you have a range of 30 meters, it's going to be equal to how many centi? 3 centimeters. It's going to be very small, okay? Instead, you can change the scale. For every 5 meters, you can graph 1 centi. So that if you have 30 here, your graph here will become 6 centi. You can choose your own scale, okay? I will give you a second option. But before I do, let me go to the Telegram. Okay. If you remember, I sent you the video link. I also send you a second video. This video shows you how to graph using a scale. Okay. As of 10. Okay. If you review this, you can actually, even the scale is there. You can actually make a graph by pencil. You can see at the end of the video there, I have my 2-3 graphs by pencil. Okay, so that's option A. What about option B? If you want option B, you can print the graph. Okay, but because we are submitting by Blackboard, our lab report, you can save it as an image and then you can upload it with your report. So what are you going to do? All the angles, let's erase this one. 75, okay, 75. What else? 60, 45, 30, and 25 with the complete lines like this. You can also make screenshot and then attach this screenshot. Okay, how do you make screenshot? Usually I will use the snipping tool. This is my snipping tool here. Okay. And I will take screenshot like this. And I can write my name. Oh, not from there. In an empty space. So Timothy. And then my ID number, 432727, something like this. And attach it to your PDF report. So whichever you want, by pencil or you want by screenshot, you can submit your graph. If it is by screenshot, you must have all the lines. Is that clear? All the lines. So this is 75, this is 60, 45, 30, and 25. The number of degrees must be shown. Yeah, it's better if you can show me, okay, so that I know. But for me, I don't need. I want you to learn it, okay? Something like this, attach it as part of your report, then it will be acceptable. Any questions? It's so easy. Projectile motion is very easy, okay? Yes, Saeed, you have questions? What's the effect? Okay, if you have no questions, I want to show you what's the effect of air resistance here, okay? Let me show you the effect of air resistance at 45 degrees. Let's use 45 degrees. When you fire a projectile, okay, at 45 degrees, what's gonna happen? Oh, come on, Canon, it's hard to set it. There you go. Let's fire at 45 degrees with air resistance. Boom. Whoa, where did it go? There you go. If you remove air resistance and fire again with the same angle and initial speed, you will see that there is a small difference between them. Can you see the small difference between the lines? I cannot move this one. Come on. There. You can see the two lines at the end, okay? Because the air is slowing down the projectile by absorbing some of the energy, okay? And this is more observable if the diameter of the projectile changes. So let's say we make the diameter half a meter like this, okay? And we fire again. That's without air resistance. With resistance, you will see that the diameter affects. And this is, you are correct. Saeed is correct. This is a source of error, okay? What about them? It's a source of error. This one, the one I'm discussing to you. Air resistance is a source of error. Why? It affects the projectile, okay? So if we go to the source of error, number one, down here, you can write it here, source of error, air resistance. Here, source of error, air resistance. What's the precaution? You have to remove the air resistance. How do you remove air resistance? You have to put the experiment in vacuum. Is that clear? Is that clear, everyone? What about the others? Only Said, Mohammed, they're the only ones answering? Put it with a cover? Yes, but if there is air inside the cover, you have to remove the air. That's the important part, okay? There must be no air. Now, what about, one student, he said, what about we do the experiment in space? That's fine, there is no air in space, but there is also very small gravity. If you look at the effect of gravity, okay, what happens if the gravity is less? The same everything, no air resistance. If the gravity is less, the projectile will be more. The range will be more. Because, as I told you, it's the gravity that's pulling the object down. Okay? If the gravity here is 0, the projectile will simply go in a straight line and go to space. That's the idea. Okay? So if there is no gravity, the projectile will go straight into space. Okay? Now, let's continue with our source of error and precaution. Another source of error that you can make is, of course, if the angle of, I forgot to click my typewriting tool. If the angle is not accurate. If the angle is not accurate, okay? In the lab, it's actually very hard to set this angle accurate. This one here, okay? So the best way to do it is to set the angle carefully. So you have to, again, typewriter, set the angle carefully. If the angle is not accurate, does it affect the projectile? Of course. So let's say you are making 60 degrees, firing, okay? If we make the angle not accurate, let's make it 59 degrees, you can see that it has a different effect, a different range, and a different height, okay? What else is a source of error and precaution? We can review in the book some of the source of error and precaution. For example, as a precaution, you have to wear goggles. This is true if you are doing the experiment in the lab. For simulation, you don't need it, so don't write it in the report. Do not place other objects in the launcher. This is true, okay? But again, we are not using the launcher in the lab, so this one, you cannot write it. Do not look in the launcher, again, true. Do not aim the launcher at others, that's true, okay? Fire the ball at minimum speed, that's because the launcher we have in the physics lab has 3 speed, 1, 2, and 3, okay? Measure the launching angle accurately. This one, we write it as our second source of error, precaution, okay? The launching angle. There, the angle is not accurate. What about the last one? Catch the ball after it hits the plate so it will not hit other things or get lost. Also in the lab, so you cannot use this one, you cannot use this one in this report, okay? What else can you write as a source of error and precaution? Start with the initial height 0. Okay, that's good. Okay, let's go to the lab manual and let's see it. What's the source of error? The initial height, or you can say the launching height is not 0. So you must start with 0. But this will not affect the experiment itself. It will affect only the maximum range. But it's okay, it's acceptable. What else? Anyone? What else? You must, here, again, like I said, you must, the gravity must be 9.8. Okay? If the gravity is not set at 9.8, let's say the gravity is 20, that's in Jupiter or in Saturn. What happens? There. If the gravity is 15, okay, if the gravity is 9.8 and so on, and if the gravity is 0, the projectile will go to space. Okay? So, any questions about the report, Shabab? Any questions? Again, you will submit the report in Blackboard, okay? And please, make sure it's PDF. Do not submit Microsoft Word. I cannot check it easily in Microsoft Word. It will be downloaded before I can check it. Not like PDF. PDF, I can check it directly in Blackboard. Yalla, Shabab, any questions? That's it. That's our experiment. Like I said, very easy. We finish in 1 hour. Okay, if there is no question, I will check the attendance now. Wallahi, I hope that nobody went to sleep because it's so easy. Let me just wait for the text message from JIC. Okay, you can see again, the attendance is here. So please get ready to answer, okay? Including Muhammad 314. Muhammad 314, are you here? Ahmed Samir. Okay, so I will remove this absence, okay? Oh, by the way, I can stop the recording now.